Hello, everybody, and welcome aboard. It's Rob from PMDG. Well, we're finally going to get around to that takeoff I've been promising. Got a whole bunch of stuff to cover. It's going to get kind of busy. Don't let it worry you. Go back and watch this over again as many times as you need. So without further ado, let's get started. So here we are on the flight deck of the PMDG Douglas DC-6. We're holding short of runway 22 at Washington National Airport. Oh, and by the way, you probably noticed in the beginning credits I've been plugging this scenery. I really like it. I live right up the road from here, and I've worked at this airport. I saw the terminal build. It's a great piece of scenery. I highly recommend it. All right, so let's dive into our tablet here. I just want to point out the weights we've got set, and this is going to be important for a very specific reason. I'm bumping right up on a limit that we're going to talk about. We've got 34 passengers, 2,300 pounds of cargo, 86,379 pounds. And that includes the 16,500 pounds of avgas we have on board. That'll take us quite a distance from here. All right, so it's time to start getting settled into the takeoff. Now, as you're getting used to flying the DC-6, we strongly recommend that you use the automated flight engineer. You can do all the power setting yourself, you can do all the switches yourself, you can do all the knobs yourself, you can do all the levers yourself. But as you're learning how to do all that, we recommend you use the automated flight engineer. Now for takeoff, we've got three things that we can do here: a before takeoff checklist, a takeoff dry, or a takeoff wet. Now, wet or dry takeoff has nothing to do with the pavement condition. It describes instead whether we are injecting water into the combustion process in order to increase power output from the engines while reducing the amount of heat retained. You can see the water pressure indication here, and these green lights here will tell you if we're actually actively injecting water into the engines. Now, the switches to control that are up here, and when we get all the way up to high takeoff power, above 49 inches of manifold pressure, those switches will control valves that will open and start adding water. All right, let's talk about wet versus dry. The best thing to do is just simply show you numbers. It really becomes evident why we have this option here. All right, a wet takeoff at takeoff power will give you 2,400 horsepower. A dry takeoff will only give you 1,950 horsepower. The manifold pressure that we can reach with a wet takeoff is 59.5 inches. With a dry, it's 53. Our maximum takeoff weight using a wet takeoff is 103,800 pounds. But with a dry takeoff, it's only 87,600 pounds. So the advantage that the wet takeoff is giving us is that it is giving us a significantly higher maximum takeoff weight by improving the thermal process of combustion inside the engine so that we can get more power for the same thermal signature. And that means we can get more power out of the engines with less heat absorption in the cylinders. As we've talked about, heat absorption in the cylinders ultimately leads to excessive wear. So, how do you choose between a wet or a dry takeoff? Easy. If you're above 87,600 pounds, that's a wet takeoff. If you're below it, it's dry. Simple. All right, we're going to do a dry takeoff, but I do want to show you on the gauge what it looks like. If you look here, right where my pointer is, at the 53-inch mark, there is a red line. That is your maximum manifold pressure when operating dry. If you then look down to where the 60 is, you'll see that there's another red hatch mark, and that one is at 59.5 inches. And that's your maximum takeoff power when you're operating wet. Again, if you're over 87,600 pounds, you're going to go wet. If you're under it, you're going to go dry. There's really not a whole lot of fudge to it. All you got to do is remember that number. All right, well, there's one other number you got to remember, and that's the 86,400 pounds that we weigh right now. There's no fancy FMS on this airplane. We got this little placard glued to the ceiling to tell us what our weight should be. So looking at it, 86,400 pounds, we'll round it up to 90,000. And this row right here is telling us what our speeds are going to be. So get my pointer out here. Okay, there we are. So at the 90,000 pound row, from sea level to 2,000 feet, our V1 speed is going to be 92 knots. And our V2, and also rotation speed in this case, is going to be 107 knots. And just for a frame of reference, the climb speed for this airplane is always 165 knots. Shifting our attention now to the takeoff, we're going to use the automated flight engineer to run the before takeoff checklist while we move the airplane to the runway. Again, the flight engineer is there to make our lives easy while we drive the airplane.
First bumps.
Now, as they begin their tasks, we're just going to add a little bit of power, release the parking brake, and start putting the airplane on the runway. I do recommend, if your runway is less than 5,000 feet, make sure you take good care turning onto the runway because you're going to want every inch of it. Generally speaking, what you're afraid of is not losing an engine on takeoff. It's losing an engine before takeoff and having to stop on the available runway left. Brakes on these older airplanes are not what they are in a modern airliner, so you don't really have great stopping power. So you want every inch of runway available to you.
Closed and on. Controls.
Now, once they finish up their task, the flight engineer calls out that the checklist is complete. At that point, we'll be ready to take off.
On. Mixture and cowl flaps. Reach and locked. Set. Transponder. On. Landing lights. Extended and on. Before takeoff checks complete.
So the automated flight engineer has got everything set. He's ready for takeoff. Now that we're in position, we'll make a quick review of all the engine gauges just to make sure everything's set the way we want. What we're going to do is, most importantly, take a quick glance at the flap position indicator to make sure the flaps are actually at 20 degrees. That's right there. If your flaps aren't at 20 degrees, this takeoff's going to take a lot more time and distance than you really planned for, and that's not a good thing either. So, before we turn him loose on the takeoff check, we'll just glance across, make sure all of these needles line up so that all four engines look the same. Again, we want to go through the second row. We should have just about the same indication on all the engines. You can see that our cylinder head temperatures are fairly cool. Everything looks pretty good. So let's talk about the power settings that are going to be used. Now, your flight engineer is going to manage these for you, but I do want you to understand what he's doing. We have three power settings that are going to be used on takeoff. We've got takeoff, we've got METO, and we've got climb. Takeoff for this one's going to be 53.5 inches and 2,800. He'll then bring the power back to 48 inches and 2,600 right after takeoff. Then once we get established in the climb, he'll set the power to 40 inches and 2,400. A lot of people have been wondering what METO means. It means maximum accept takeoff. So to give you an idea what this looks like, we use takeoff until really we've left the runway. Then we switch to METO. We use that for the initial climb while we're pulling the gear up. Then we switch to climb power, and we'll use that all the way up to cruise altitude. So those three power settings, that's what your flight engineer is going to give you. Okay. Let's go ahead and tell him dry takeoff.
30 inches stabilize. 30 inches stabilize.
This 30 inches and stabilize call is an instruction to the flight engineer to bring the engines up to field elevation pressure, which is usually about 30 inches. Once he gets them up to 30 inches, we're then going to do a quick glance down at the RPM gauges and make sure we see 2150 RPM or so. That tells us that the engines are developing correct power.
Full power, please. Going full power?
Now the flight engineer is starting to advance the throttles to full power. Once he passes 40 inches of manifold pressure, release the parking brake. Your job now is to keep the airplane on the runway. If an engine quits at this point, or you hear a loud bang, a vibration, or you have a controllability issue, pull the power to idle and apply maximum braking. Steer straight ahead. Don't worry about trying to clear the runway. Your job is to stop the airplane. All right, we're approaching 107 knots. Okay, hold on. Just stop. We need to do a quick briefing for all you jet pilots. So gather round. Let's have a talk about technique. One of my favorite pastimes is to watch YouTube videos created by some of the groups that are around Digital Combat Simulator. There's groups like, my favorite is the Grim Reapers. Cap and the guys put on a great show. But when they get into the World War II airplanes and start flying, you can pretty much guarantee that you're going to see something that looks like this. Ow. Now that's going to be a lot of paperwork. Okay, why does that happen? Well, it's about technique. You see, swept wing airplanes have all kinds of flaps and slats hanging off of them, specifically because swept wings are horrible at low altitude. A straight wing, like a DC-6, actually is most happy at low altitude. A DC-6 will barely need to rotate to leave the ground at its appropriate takeoff speed. A jet needs to pitch up to anywhere from 9 to 14 degrees depending on the airplane type. And so a lot of jet pilots, when they hop into a straight wing piston pounding World War II era airplane, they go and rotate that thing really hard and, well, yeah, okay, that's what you get. So let me show this to you graphically just to give you an idea what we're working with. Here's a bar graph. We got altitude, we got distance. We draw in a swept wing airplane. Don't laugh at my artwork. I'm a pilot, not an artist. Okay. When a swept wing airplane is going to take off, it's going to rotate to somewhere between 9 and 14 degrees, depending on the type of airplane it is. It looks kind of like this. So we'll put a little landing gear on there. You can see the nose is high in the air. There's a tail. I told you I'm a pilot, not an artist. A straight wing airplane, on the other hand, go ahead and make these wings straight, put little engines on them. Looks like a DC-6, don't you think? All right. When a straight wing airplane leaves the ground, it's got very, very little rotation at all, maybe a couple of degrees. What that looks like in the climb profile, the jet is going to accelerate like mad, and it's going to turn all that excess acceleration into climb. That's the beauty of jets. A jet on takeoff will hit 165 knots about here, and then it's just going to pitch up and use all that energy to climb up. Our straight wing DC-6 isn't going to hit 165 knots till it gets way out here. That's a really shallow climb angle. And if you don't expect it or you don't know that that's what's going to happen, it can really throw you off. If you pitch the DC-6 up to 14 degrees, you're going to run out of airspeed, and yeah, that's going to make you unhappy. So let's not do that. The first time I fly passengers on the DC-3, a lot of times the thing that gets their attention the most is that the airplane seems to have a nearly level deck angle as it starts to climb, and it maintains that through the entire regime of flight. You control the climb and descent, really, using speed. The DC-6 is going to be very much like that. So, all right, let's go back to our takeoff. Now, I want you to watch the attitude indicator really closely. We are going to pitch up just slightly, and then the airplane is going to just levitate off the ground. Now, there's a little bounce in the runway right there. It's kind of annoying. It hits at exactly the wrong moment, but you can see that I'm maintaining pitch steadily at about 5 degrees nose up. And the end result is that the airplane is really doing a great job of accelerating. You can see the needle moving as we start to approach 140 knots. The flight engineer is starting to clean things up. He's raising flaps and gear. Our climb rate is holding steady at about 500 feet per minute, which doesn't seem to be stellar. But once we get to 165 knots, I can then start to convert that energy into climb. So you'll see now that we're at 165 knots, I can pitch up a little bit, and our climb rate jumps up to about 1,500 feet per minute, and then things start to go really well. This is why it's important to know if you've got rising terrain in front of you when you're flying an airplane like the DC-6, because you might not be able to outclimb it. That's also bad. All right. Now you'll notice if you look over at the engine gauges, our flight engineer has brought the power back progressively through METO, and now he's back to climb power. He's got 40 inches of manifold pressure set and 2,400 RPM. Our fuel flow right now is running about 1,200 pounds per hour times 4 engines, so we're burning just about 5,000 pounds of avgas per hour. This stuff costs about $8 or $9 a gallon. All right, so we're still climbing at 165 knots, a little over 1,000 feet per minute. Engines are happy. We're cleaned up for the climb. Things are really looking good. Fuel flows are happy. That little split that you see right there is normal because the engines are each a little bit different from the other. But let's go back and take a look at that rotation again from a different point of view. Looking at it from the outside, see that tiny little bit of rotation? See how the airplane just sort of floats off the runway? That's the proper technique for flying a DC-6. You don't want to pull the nose up real hard, or you're just going to slow the airplane down and get yourself behind the power curve. If you lose an engine, it'll kill you. So watch that rotation again. See, just a tiny, tiny bit, and you just wait for the airplane to fly itself off. One more time. Tiny rotation, the airplane just kind of floats off the runway, and you're on your way. Last time, see it again. Tiny, tiny, tiny rotation. There you are. And patience, it flies away. Then you just want to hold that pitch attitude. The airplane will take care of the rest. All right. That's enough for now. Thanks for flying, PMDG. Fly safely. Be well. Look after one another. We'll see you next time.